We are live. Good morning, everyone. Thank you for joining what promises to be an exciting webinar on grid resilience. This webinar is hosted by the CIGRE NGN Belgium in collaboration with the CIGRE NGN UK. And my name is Emmanuel Sule, a PhD researcher from the KU Leuven, Belgium, also Energieville in Genk. And I'll be moderating today's webinar. And I'm thrilled to have everyone here joining. Today we'll be learning a lot on grid resilience, and also we'll be focusing on some recent happenings, such as the Heathrow power outage and the Iberian Peninsula blackout in the last months. And I hope it's exciting for everyone. About what to expect from today's webinar, we should expect presentations from experts in the field. We have a professor from the University of Valencia and also power consultant from ATROP UK. And I want to encourage that we actively participate in this webinar, as we would have questions and answers after each session. And then I would quickly show right now what we plan to do. Show an agenda, and I hope now you see my screen. So after my opening remark, I will have the president of the chairman of the CIGRE Belgium NGN tell us about the NGN. Also, we'll have our colleague from the UK talk about the CIGRE UK NGN as well. And then we'll have a first speaker who would be talking more on power resilience in the UK. And then we'll have a speaker from Spain who would touch more on the Iberian Peninsula Blackout, and then we can ask the questions. The mics will be unmuted after each section so as you could audibly ask questions, and also for those who would want to ask questions via the Q&A chat, you could also do that as well, and we'll try to attempt and answer all the questions that are presented today. So I would hand over now to Oscar to give an overview of the CIGRE Belgium NGN.
All right, thank you, Emmanuel. So indeed, this webinar proves to be very interesting. I thank you all for being here, and I will start with an introduction of the Belgian NGN. So to start with, what is CIGRE? CIGRE is the Conseil International de Grand Réseau Électrique. It's an international council on large power systems, and its core is really to share power system experience and expertise. Now, CIGRE has different national committees. It's a large international organization, and as such, it also has a Belgian national committee under which there is the NGN Belgium, which is the next generation network. So the Belgian Technical Committee is split up over several study committees, and CIGRE, as it is really intended to share power system expertise, it has these different study committees that brings together experts which work together to really figure out questions, address challenges in the field, and they work together in the working groups that in their turn develop the technical brochures that are so well known, and these appear on eCIGRE. So CIGRE has the national committees, the study committees, but also the conferences, the largest of which is the CIGRE Paris session. And there's also colloquiums, smaller conferences. So CIGRE is a very large, very well-established organization that brings together a lot of experts, which is very interesting, of course. Then the study committees are split up into 4 groups: equipment, technologies, systems, and materials and IT. And I will not go over them all, but this is just to give you an idea of the variety of technical questions that are addressed, and really the scope of the expertise that CIGRE brings, and the scope of the professionals that CIGRE brings together. So as you can see, there's a lot of variety in the subjects, a lot of very electrotechnical, very deep knowledge on materials, but also on the system level, there's a lot of research, there's a lot of experience. So any power system professional, I think, can benefit from keeping up with these study committees. And then this brings me to what is the Belgian Next Generation Network. The Next Generation Networks are networks under 35 that are embedded within the national committees. And so the Belgian Next Generation Network is really a network of younger power system professionals under 35 that are a part of both CIGRE Belgium and the wider CIGRE community, with the result that we can organize webinars such as today that bring together people from NGNs of different countries, which makes it, of course, all the more interesting. So what does CIGRE bring for young professionals? And this is really, I think, the value of CIGRE now, and it's a very interesting period of time to be a part of CIGRE because we really have historical challenges. If you look at the power system, both the European Union and the UK have pledged to be carbon neutral by 2050. And so if you're under 35, this means that the power system must be carbon neutral before we retire. And this is, of course, a monumental challenge, but it's also a very large opportunity because we can address really fundamental questions about the power system. These are technical challenges that are, in my opinion, really historical. And it's also our opportunity to play a significant role in such a big project and in such a big challenge. So Europe and the UK are really the places to do this because we have very advanced climate policies, very reliable grids, and we can really be at the vanguard of these developments. So this is really a historic time to be in power systems and to work on these topics. And then CIGRE, how does it come in? As an organization for sharing power system knowledge, it really sets the pace for how we learn, how we develop our expertise, and how the sector evolves, because CIGRE brings around and transmits also this knowledge among experts, and as such, it really sets the pace for how fast the sector learns. And as you saw, it has a lot of faces, CIGRE. It has the conferences, the study committees, the national committees, and the NGN is really the perfect place to enter this network and to get your foot in the door and to get started in this system. All right. Then, as I mentioned, CIGRE really helps for young professionals in the first place to access all the expertise that already exists, but it also gives you access to an online library that has all these technical documents, and through CIGRE, the expertise that you develop in your fields and in your groups also ends up in the right place. All right, I will skip a bit further over this. Our NGN in Belgium is mostly made out of academic members, which means there's a lot of place for industry. We are continuously looking to expand our membership, and of course you can be quite a big part of this. So the Belgian NGN was only started in 2021, so we're quite a young organization still, and we're really looking to expand our membership. What are the benefits of joining the NGN? Well, as I mentioned, CIGRE is really the online library where all this technical expertise comes together. So as a young professional, it's a fantastic resource to really get a view on what other experts are thinking, what other professionals are thinking. And you really see the timeline of how the sector has addressed different challenges, different questions. So it's fantastically interesting for new professionals. But there's also really the network of people that you can access through your engagement and your participation in CIGRE events. You can really get to know people, pick their brains on questions, and expand your network in this sector. So activities we do range from technical visits, such as the ones in this slide. We visited the Hoboken shipyard for offshore substations, but we also visited the battery system. So it's very varied what we do. And as you can see, with each technical visit, we also organize a round of presentations, really to facilitate this knowledge exchange among our members. And being from academia and industry, this makes for a very interesting exchange of ideas, and we can really put together different perspectives on the same topics. Then there's also the annual presentation competition. So yeah, as you see, there's really a variety of events. So really, we're continuously looking to expand our membership. We're a quite young organization, and we'd be very happy to welcome new members. And this is how you can sign up. So you go to the CIGRE Belgium website, become a member of the national committee, and then you can join the NGN. So thank you for listening to the introduction. This is, of course, only the start, and I will now hand over to my colleague from the UK to introduce the UK NGN.
Thank you, Oscar. And thank you very much for the great presentation and introduction into CIGRE as well. So hello, my name is Yavuz Korman, and today I'm going to give a brief introduction to UK CIGRE NGN. So let's start with CIGRE UK. As Oscar has explained it quite very well, it's a professional organization network in UK. It's a community of engineers, researchers in the field of power systems, essentially, and it provides most up-to-date technologies and resources such as technical brochures. There are 16 study committees, as has already been mentioned, and there are many, many working groups as well. So what is CIGRE NGN? So NGN, which stands for Next Generation Network, is a network for the professional, young professionals, young engineers and researchers under the age of 35. You will find the connections, the knowledge and the confidence that you will need to advance your career. And you can also say it's almost like the gateway to CIGRE as well by joining the NGN. So essentially, the purpose of NGN is to facilitate a successful transition into the power systems industry for young professionals, and it gives you a great opportunity to network and discuss and collaborate with other young professionals. How you can get involved? You can become a CIGRE UK NGN member by following the links on the page that is here, and you can also easily scan the QR code on this slide to become a member. So I will briefly go through the organization chart of the NGN in UK. We have a couple of positions in the NGN where we have a chair, vice chair, secretary treasurer, and other roles. We have a couple of teams in the NGN, such as membership team, which I'm the lead of, communications team, events team, technical team. And there are also university hubs, which I will go into detail in a bit. This is a brief introduction into the team and our members essentially. They are from various couple of different companies and universities as well. You can see our members as well on this slide. Moving on, the benefits. So when you join the NGN, as I already told you, you join a community, and within this community, you can develop the skills such as working as a team, your communication skills, your time management skills, and all of these basically help you towards your professional and personal development. So when you get involved in NGN, you can access all the CIGRE technical brochures, e-CIGRE, you can join the international working groups. There's currently recently a mentoring scheme as well, which has just recently been announced as well. And there's steering committees and working groups as mentioned. And the key thing here is you need to remember, you do not need to be an expert to join. This is specifically for young professionals. I just want to mention a couple of our past NGN events. We had a webinar on hydrogen electrolysis plants. We had a presentation competition in Manchester, and we had a collaboration with study committee liaison meeting. We had an exciting visit to the brush transformer factory in Loughborough, where we have been briefed about the design of the transformers, and we have got a very nice factory tour and knowledge on how transformers are being manufactured actually. There have been many more events which you can find in the website of CIGRE UK NGN, which I put a snip here. I will tell you in a bit how to access this website as well. I also want to briefly mention the university hubs. So what is the CIGRE UK University Hubs? These are university-based communities, essentially, within CIGRE, which support and enable the next generation of power system professionals. These are more local communities and for people to collaborate and get together locally within their universities as well, and within these hubs where they can discuss topics, network with each other, discuss and collaborate on research and projects. If you want to get involved for the Midlands region, you need to contact the email shown for London region and the Northwest region, which is currently in preparation of being prepared, essentially. This is some pictures from our team in the CIGRE Paris event. And to finish off, basically, you can go to the events page shown here by scanning the QR code or following the link on the slide. And you can see our upcoming events from here. An exciting upcoming event actually for us is a visit to the National Grid NISO Energy Control Room. And it's a great opportunity for people interested as well. You can follow the LinkedIn and our newsletter as well for any updates. Thank you very much for listening in, and I will pass on to my colleague. Thank you.
Good morning, everyone. Thanks for the invitation from the both the NGN, CIGRE NGN from Belgium and the UK to give me the opportunity to briefly talk about power system resilience in the UK, focusing on few events in the recent years and so far what has been happening in the industry in the UK. To begin with, I'm a chartered engineer, a principal consultant, currently working at Arup within the energy advisory team. I mostly work on design, due diligence, and master planning for different critical infrastructures, focusing on their electrical engineering systems, both in public and private sectors. Owing to my academic background, I also participate in many industry-driven innovation projects. And prior to joining Arup, I have over 7 years of experience researching the British electricity system and its resilience. So what am I going to talk about today? I structured my session around 4 questions. First is to talk about how are our daily life affected, which will focus on 3 very recent and impactful events. First is the power disruption incidents in London in August 2019. Secondly, focusing on more climate weather-related event, Storm Arwen, at the end of November 2021. And very recently, in March, we've had a fire incident at the North Hyde substation in 2025, basically led to very major disruptions to both energy consumers as well as a major national infrastructure, the Heathrow Airport. After looking at how our life is going to be affected, I want to briefly touch on what does resilience mean for infrastructure systems. Basically, I'll focus that on the framework proposed by the UK's National Infrastructure Commission. Following that, I want to talk about building on my innovation background, and then to give a little bit of background context on what have the network owners and operators been doing in the UK, specifically focus on quite organize 3 topics. First is the climate resilience demonstrator, Credo Plus, which is led by UK Power Networks. Secondly, looking at another major initiative called Predict for Resilience, which is led by Scottish Power Energy Networks. Lastly, from a transmission system side, I want to talk about the Forward Resilience Measures project, which was led by National Grid Electricity Transmission. And I want to end my talk on the question. I don't think we have a definitive answer, but really want everyone, especially our young professionals, to take that away around what is the key to unlocking investment in power infrastructure resilience. So without further ado, how are our daily lives affected? So this goes back to 2019. A lightning strike occurred on a transmission circuit at about 4:52 p.m. on a Friday, 9th August. And as a serious event happened, and that led to, in total, 1.1 million electricity customers without power between 15 to 45 minutes. And the impacts to other critical facilities, including hospitals and Newcastle Airport, are very, very significant. And a major part of that disruption is to the rail network. This includes blocked lines, wide cancellations, and significant delays, impacting thousands of passengers. So in total, there were about 371 services cancelled, and another 220 services partially cancelled. And a major contributor, and in my own opinion, is a bit of a disappointing point, is around a disruption to a particular class of trains that operates in the southeast area of the UK. Approximately 60 trains unexpectedly shut down when the frequency dropped below 49 Hz, and half of those trains require a visit from a technician to get restarted. So this has caused major issues within the rail system, and that really caused a lot of the hazard. And on screen, it only captures one of the occasions that passengers had to be evacuated from the trains and walk along the tracks to basically leave the train. So diving into a little bit more detail, so how has everything happened? As I said, when the lightning struck, it caused a fault on the 400 kV lines, and this was nothing extraordinary and was rectified by the protection systems within 80 milliseconds. But this has led to impact on local distribution networks with initial disconnection of 150 megawatt of distributed generation because they have to be traded off due to a safety mechanism known as the vector shift protection. And following that, the voltage control system at the Hornsea 1 offshore wind farm did not respond to the impact of the fault on the transmission system as expected and became unstable. And that led to a rapid reduce of its power generation. In essence, it has been reduced from around 800 megawatts down to 62 megawatts. So that is over 700 megawatt of reduction. And then very shortly after that, the steam unit at Little Bafford Power Station in Bedfordshire, which is rated as 244 megawatt, disconnected from the transmission system. And the speed sensors on the steam turbine produced the discrepancy, basically, and initiated its automated control system to shut down. So this so far has led to a total loss of power generation for more than 1.1 gigawatt within just 1 second of the fault. And as a result of that, a further estimated around 350 to 430 megawatt of generation being tripped off unnecessarily. And around a minute after the fault, one of the gas turbines, again at the Lato Buffered power station, which is about 210 megawatt in total, has been shut down for safety reasons. This is due to too much steam pressure built in its pipe works. So this then led to the total loss of generation to coming up to just shy of 2 gigawatt. But fortunately, the system frequency, although suffered a huge dip, as you can see on the screen, but managed to return to 50 Hertz within about 5 minutes of the fault. And all electricity supplies were restored through the local distribution networks within 45 minutes of the fault. So although magnitude-wise, this is a significant disruption, but from a time horizon-wise, all the supplies were restored relatively quickly. But as I was saying before, the key thing is related to the knock-on impact on the trains, because some of them need technicians to visit on site to get into the trains to get them restarted. So what have we learned from this event? System security need modernization. Counter state standards is not sufficient for low inertia and high distributed generation environments. The system lacked robustness against rare, but although credible N-2 events. Also looking at real-time inertia and frequency visibility, that's a key thing for the system. Also looking at the scheme for low frequency disconnection of demand schemes is outdated. Basically, they are based on preset thresholds without the necessary coordination with distributed generators. And also protection settings are too rigid, as I mentioned earlier. DNO's actions were a bit of inconsistent, especially around how the critical demands being disconnected. And also there's the lack of cross-sector coordination, as I was saying, in terms of the knock-on impact with the critical infrastructure like the rail traffic systems has suffered really fall behind of the restoration timescale. So correspondingly, what are the recommended actions? First is looking at updating all the standards and stability planning criteria. We need to try to improve visibility and forecasting tools with the capability of looking at the system's inertia. We need to modernize or upgrade the low frequency demand disconnection schemes. We need to harmonize the distributed generation protection standards, enhance DNO and TSO transmission system operators coordination, and also conduct system-wide black start and DG response simulations. I think another part of that is integrate critical infrastructure planning. I think that is a really key lessons learned, and the key recommendations out of this review is include transport, telecoms, and emergency services in restoration protocols to absolutely try to minimize public disruptions and safety risks. So that's the event happened in 2019. Coming to 2021, Storm Arwen brought severe wind to the UK towards the end of November, with the Met Office issuing a red warning for wind. Wind speed widely reported to reach over 70 miles per hour, with the highest gust speed measured to be around 98 miles per hour in Northumberland, in the northeast of England, basically. According to the Met Office, this was one of the most powerful and damaging winter storms of the last decade. So inevitably, this had a significant impact on the electricity distribution networks. Storm Arwen brought considerable damage to most of our distribution networks across the country. And in some areas, severe wind were accompanied by snow, ice, and rain. The damage resulted in over 9,700 faults, which were primarily caused by strong winds and fallen or broken trees. So following from that, over 1 million customers lost power as a result of the network fault and damage. Most customers were restored reasonably quickly, with about 82% of the customers reconnected within 24 hours. However, many customers endured longer power outage. Around 40,000 customers were without supply for more than 3 days, and nearly 4,000 customers were off supply for over a week's time. In Northern England and Scotland, numerous power lines were damaged by fallen trees and broken poles. As you can see on the screen, a general different types of the network faults being collated. Most of them are due to strong wind, falling trees, but there's also a fair amount attributed to wind-borne materials and also wind and the suspected ice accretion. And as I was saying before, around 40,000 households experienced outages for more than 3 days, and nearly 4,000 households were without power lasting over a week. Unfortunately, in the Northern Power Grid area, which is the really dark red area you can see on the right-hand side, sorry, some of the outages lasted between 6 to 10 days. So what lessons did we learn from here? Emergency preparedness gaps. The emergency plans of some DNOs were not sufficient. There's limited fault visibility. This actually links to a project I'm going to discuss later on. Lack the visibility of faults, especially in low voltage networks. DNO were under-prepared for wind from an atypical direction. In effective customer communications, this appeared to be have a significant impact, especially emotional impact on consumers as well. That's why following Storm Arwen, the DNOs across UK would draw in resources from all their teams to participate in communication with their consumers during emergency or severe weather events, just to provide the right communication and support to the different customers that are wanting to communicate with, get in touch with the electricity utility company. There's also a touch upon inadequate compensation mechanism, and then I guess a little bit surprising as well, poor vegetation and infrastructure resilience has been highlighted as one of the lessons learned. Accordingly, recommended actions is strengthen winter preparedness planning, enhance fault monitoring and detection. That leads on to what the project Predict for Resilience is really trying hard to do. And then looking at improved customer community systems, as I mentioned before, early on, that more people from across the teams within DNO's organization will be participating in customer communications during severe weather events. Modernize the compensation framework, invest in network resilience. This is a really key point worth emphasizing, is invest in network resilience and also coordinate with local resilience forums. That goes a lot wider than just electricity systems. It goes into community level, how local authorities and the local charities and everyone could be coming together to build out those joint responses to resilience. And now we come to 2025. On Thursday, 20th March, just 14 minutes before midnight, one of the 3 supergrid transformers at North Hyde substation caught on fire, and its associated circuit connecting to it to the wider transmission system tripped. And shortly after that, the adjacent transformers also tripped, resulting in simultaneous loss of connection to the remaining transformer. The consequence was the total loss of all supplies at the North Hyde substation, impacting thousands of customers, including Heathrow Airport. Using forensic analysis from both the National Grid Electricity Transmission and London Fire Brigade, this review has seen evidence that a catastrophic failure on one of the supergrid transformers, high voltage bushings, caused the fire to ignite on the supergrid transformer. This was most likely caused by moisture entering the bushing, causing a short circuit. The electricity likely then arced, which combined with air and heat to ignite the oil, resulting in the fire. So the resulting outage led to 71,000 domestic and commercial customers losing power, and the complete loss of supply to part of Heathrow's airport to its private internal electricity distribution network. Heathrow Airport took the decision to close the airport due to the impact of this outage. And in the early hours of 21st March, the decision taken by the airport, approximately 90 minutes after the power outage, they decided to stop operations immediately, and in order to protect the safety and security of people, as well as the integrity of the airport, as well as the UK border, as Heathrow is a major international airport. It then fully reopened on 22nd March. So there's a closure for around a full day. So significant disruptions were experienced by approximately 200,000 passengers, including those planning to depart from Heathrow on Friday, 21st March, and those who were already traveling to Heathrow on long-haul flights, which had to be diverted. So as I was saying, an elevated moisture reading in one of the transformer bushings had been detected as the possible cause of the fire. But this actually, the elevated reading had been detected in oil samples taken in July 2018. According to National Grid Electricity Transmission's relevant guidance, such readings indicate an imminent fault and that the bushing should be replaced. While the reading was recorded in the online system, the mitigations appropriate to its severity were not actioned. This is a bit unfortunate. The controls in place were not effective and failed to identify subsequently that action had not been taken in relation to the elevated moisture reading. This includes an opportunity in 2022 when a decision was taken to defer basic maintenance on that transformer. The issue therefore went unaddressed. While National Grid Electricity Transmission's current standards for fire controls at substation sites prioritize distance and physical barriers between oil field equipment. Neither of these measures were in place at North Hyde substation because this is a relatively old substation built prior to those standards were established. Risks at the North Hyde substation were managed by National Grid Electricity Transmission using multiple separate processes, meaning there was no single structured process to provide a cumulative assessment of the overall risk for the whole site. So following that, National Energy System Operator has published its final report in regard to this incident. And within that report, multiple recommendations has been put forward, mostly focusing on asset management systems, fire and asset risk assessment, resilience of infrastructure with multiple supply points. That is a bit focusing on the airport side because they essentially had 3 separate connection points with the local electricity networks, but they didn't manage to take the full advantage of that 3 separate connections, and hence there's also the following recommended action around energy resilience and of critical national infrastructure. So with all those in mind, with all those events, what does a resilience mean for infrastructure systems? The Commission provide, so what I'm quoting here is from the National Infrastructure Commission, which provides the government with impartial expert advice on major long-term infrastructure challenges. And in summary, they have published in 2020 May a framework, a very milestone report, which covers anticipate, react, recover. That's what essentially what it means. All resilient infrastructure systems should be able to sufficiently anticipate risks, would be effectively react to the event, and then also having speedy recovery and potentially transformation after the recovery from the system. So in order to, so on the screen, you can see is the detailed framework proposed by the National Infrastructure Commission, and it states to deliver resilient infrastructure systems, a framework for resilience is absolutely required. And as I mentioned before, better anticipate future shocks and stresses by facing up to uncomfortable truth, improve actions to resist, absorb, and recover from shocks and stresses by testing for vulnerabilities and addressing them, value resilience properly, drives adaptation before it is too late. So from there, I want to talk a little bit more into the projects. But before I do that, a very quick background information is the Scottish Power, Scottish and Thousand and Scottish Power Energy Networks are the transmission network owners in Scotland, where whilst the National Grid is the transmission owner for England and Wales. And also there's multiple different distribution network operators across the country. And later on, we'll be talking about some of the initiatives they've been doing. So the first project I want to say is CREDO, Climate Resilience Demonstrators by Power Networks, UK Power Networks, which focus on understand interdependency and cascading risk, as we were talking about the train risks. That's kind of an example of how interdependency and cascading risk could look like, adapt to changing climate and improve overall system resilience. So essentially, CREDO is a climate change adaptation digital twin. It really tries to connect across the sectors to understand infrastructure and interdependencies. The next one, as I was mentioning, predict for resilience, is aiming at provide accurate fault insight and forecast for its users during adverse weathers. This is looking at a short term, about 7 days in advance. And the major benefit is trying to remove the reliance on tactic knowledge for risk assessment, which is not backed up by data and subject to human bias, and also trying to encourage to get away from reactive management of severe weather risks. So in order to be able to use the best information system to anticipate potential risk of upcoming weather events. And what does it look like? Essentially, on the screen, you can see is a prototype of the protocol they've produced. Is a control room. It provides control room operatives short-term predictions regarding expected level of fault in each of its districts, and in about 7 days up in advance. This will allow distribution network operator to better prepare for storm, which is, we've mentioned before, the preparedness is a key aspect, and restore power supply sooner than it is currently possible and minimize the disruption for customers. So from national grid electricity transmission, we have the Forward Resilience Measures project, which it defines, provides a definition for resilience, as we're seeing on the screen. Within that project, a holistic resilience framework for assessing physical risks for the electricity transmission network in England and Wales is produced. This enabled an improved understanding of their resilience and also the ability for them to anticipate, absorb, adapt, and rapid recover from both known and unknown shocks. And within that framework, we have gone through very thorough stakeholder engagement in order to collate the different informations. And the resilience framework essentially covers 3 dimensions: leadership, strategy, and workforce, and then focusing on community, stakeholders, and finance. And also we need to focus on environmental and infrastructure. Within those 3 dimensions, we have 12 goals defined what is needed to achieve electricity transmission network resilience. With further down associated with the goals, there are 43 indicators that can be detailedly measured. And as part of that framework, we need to also look at the physical infrastructures, and that need to both from an electrical perspective and also having the geospatial aspect. So within that project, the team were able to create storm event simulation tools that would capture how the network interacts with certain events. I think I'm a little bit over time, but just to quickly end up on the what is key to unlock investment in power infrastructure systems. So within the project, there's a strategic innovation fund project called Whole Energy System Resilience Vulnerability Assessment, which is also led by National Grid Electricity Transmission, which aims to respond to the industry's call for delivering resilient electricity infrastructure to the society. And the infrastructure assets are, we recognize, often have a long lifetime, high upfront cost, and limited flexibility. Therefore, understanding and embedding resilience from the outside is critical to ensure assets meet their objectives in terms of serviceability, financial return, as well as their social outcomes. And through that process across the initiative led by National Grid, we have drawn from stakeholder engagement and wider reviews of cross-sector practices. there's a few key lessons learned. First is transmission and distribution difference. Electricity distribution and transmission networks have different challenges in terms of severe weather impacts and different vulnerabilities to different types of event. And we recognize that in the UK, there's currently a lack of incentives for long-term resilience investment. And we then recognize the importance and criticality of embedded resilience in the overall decision-making process and what is needed to facilitate that. And finally, from a resilience, from a regulator's perspective, resilience metrics, codes, and standards will play a very crucial role as well in finally encourage and in a way incentivize the system owners and operators to properly invest in network resilience and address the challenge. With that, thanks everyone. And I now welcome any questions if you have them.
Thank you very much, Yutan. The mics are open now for the attendees. If you have any question regarding the presentation, you can just unmute and ask so that Yutan can respond to your question. Okay, thank you, Yutan. Your presentation was really eye-opening to the things happening in the UK power system network, and thank you very much. Now we'll quickly go ahead with Professor Ramon's presentation, and after his presentation, we would have a lot of time to ask questions and make the session interactive. Thank you very much, everyone. You can
thanks a lot. I'm just trying to share the presentation. Sorry about that. So you should be seeing the presentation right now in full screen. You can confirm. Excellent. Well, thanks a lot, everyone. And thanks a lot for kindly inviting me. My name is Ramon Blasco Jimenez. I'm a professor at the Technical University of Valencia. I'm heading currently the Research Institute on Automation and Industrial Informatics. We cover anything that has to do with automation and industrial informatics. So in my case, is integration of renewable energy systems. So I must say that I'm also a chartered engineer, and I did my PhD in the UK. And I also have good friends at KU Leuven. So this meeting is really nice to me for the connection with the UK and Belgium. So I think that the main idea is to talk about what happened or what we know so far about the Spanish and Portugal blackout, and see what was the role of renewable energy and some key takens. I just want to start with a map of the European electricity system. Sorry, Norway and the Nordic didn't fit quite well, but what I must say is that if you see here, the Portugal and Spain are really well meshed system. but the connections to the rest of Europe, we have only, you have a couple of 3 AC connections here, plus a HVDC connection. So the connection to the rest of Europe is not that good. So basically what it means is that we always called ourselves as an electric island. And that has quite a lot of impact on how the system is managed. The cooperation between Spain and Portugal obviously is very great on this management. Just for information, I live here, just by the seaside in Valencia, and obviously we had the blackout, and it's quite a nice. It's not a nice experience. It's quite an experience to realize how important is electricity. In about 15 minutes, all communications stop working because the mobile phones stations run out of batteries. Trains stop working, as in the UK. Underground system stop working. The only means of communication was listening to the radio. It was difficult to buy groceries because most supermarkets, the computer system and the till system didn't work. The payment didn't work on the with credit cards. So the only places you could shop was in the old shops where they did the calculations by hand and they could accept cash. So basically the main issue started in southern Spain and propagated very quickly to the whole of Spain until we had the split with the rest of Europe. So I'm going to let you know a little bit what was the characteristics of the Spanish system prior to the blackout. The Spanish system is well, the Spanish and Portuguese system have been operated at about 60–70% PV plus wind almost every day, and that doesn't match quite well with, for example, what our colleagues in Denmark are doing. But I think in our case, we don't have the ability to export to Norway or to Sweden or to Germany, so they have a much better connection. So our maximum demand is 43 gigawatts. We have 130 gigawatts total installed power, of which 8 gigawatts are embedded PV, residential and industrial. Before the blackout, we had some 25% PV. I'm not sure if you see the pointer. Let's see. Yeah. So we had a large amount of PV, not that much wind, quite a lot of hydro, about 3 gigawatts of nuclear power, and a reasonable amount of CCGT, although relatively little. At this time of the blackout, this is not true. What you see here was a total zero, but some SCADA system stopped sending proper data. So what you see here is that PV was still generated. No, PV was not generated, and even less at 12 o'clock at night. But you see, restoration, this wind is mainly real, this production of wind, but restoration was mainly carried out by hydro and CCGT. So those will be probably the main takings. What's the sequence of events? The sequence of events is prior to the event. So the day before, there were several thermal plants scheduled. Thermal plants, just to give you an idea, in Spain, by the Spanish grid code, PV and wind operate on constant Q or operate on constant power factor. So they don't participate on dynamic voltage control. So whenever there's not enough, or one of the technical reasons to schedule additional thermal plants is because of voltage or voltage control capability or frequency control capability. So one of the plants that were scheduled was taken offline by the owner for maintenance purposes on a short notice. The TSO didn't schedule any additional thermal plant because it was evaluated that with the remaining plant, it was sufficient to provide the security margins for voltage, frequency control, and N-1. Also, a big tie line between Spain and Portugal was down due to maintenance work. And during that day and in previous days, there were inter-area oscillations, 0.2 hertz, that's very well known, and intra-Iberic oscillation 0.6 hertz, which is a kind of oscillation mode that has not been seen. So those were detected by the TSO, and the TSO started to apply the standard measures to damp down oscillations. And the standard measures were reduction of exchange power with France, Portugal, and Morocco, disconnection of shunt reactors, and increased grid meshing. Something important about that is that these actions indirectly tend to increase voltage. However, before each action is taking place, obviously you have the corresponding studies. So all these actions, in theory, should have been done with the required safety margins. At 12:32:57, there's a trip in an substation in Granada on the low voltage side of the transformer, and there were more than 355 megawatts lost. 19 seconds later, there were trips on PV and thermal solar stations in Badajoz, which is also southern Spain, very, very close to Portugal, more than 720 megawatts lost. We're talking 19 seconds here. 1.3 seconds after, there was cascaded trips in the south and central Spain. We're talking more than 1.2, 1.1 gigawatts. And that was followed by cascaded tripping of generation and demand in the following 3 seconds. Load shedding was not fast enough, but it operated correctly when it reached the low frequency levels. At 13:21, the AC overhead lines with France tripped, and 24 seconds, 3 seconds afterwards, the HVDC lines stopped transmitting between Spain and France, and the Iberian system collapsed. So if you see here, from the first trip to the total system collapse was 1.5 seconds and 1.5 minutes, sorry. And most of the generation was lost between 5 seconds. So there was no way to do any kind of manual intervention. Everything should have been automatic. Initially, we were checking before the reports what happened with inertia. And inertia, basically, we were checking that there was enough inertia, definitely. We had 30% inertia before the event, and we had some 3 gigawatts fast frequency resources. So with that, it should have been enough to even to right through the disconnection of a big nuclear power station. But the amount of generation that was lost was definitely more than the 3 gigawatts in the 5 seconds. So it was very difficult to get through that. I have some examples. So that was in the morning. That's the voltage profile in the morning of the day. This is UTC, so here will be 10 European time. But you see these oscillations in the voltage that correspond to the frequencies of the modes that you can see in the frequency response. Again, during these oscillations, you see that the TSO, what they try to do is to switch off, in this case, the shunt reactors. So when it says the reactors are getting off, topology changes, which means connecting more lines, and reducing the exchange between Spain and France. The other action that has been found to reduce these oscillations is to switch the HVDC link to France to constant P mode, to constant power, instead of AC emulation. So all these actions contributed to reduce the oscillations, but also contributed somehow to the increase of power, to create a situation for the increase of voltage. Sorry. If you see these oscillations, the 0.6 hertz, clearly the generators in north of Spain were oscillating against generations in the north. So this was the internal oscillation that I was showing before. But also, as well as the internal oscillation, we had other oscillations that were between Spain and the rest of Europe. You see that all generators in Spain were oscillating with the same amplitude and angle against the rest of the generators in the rest of Europe. This is a well-known one. This is a one that is being the causes are currently being under study. What else? Rokov. Did we have trip on Rokov? What I have changed with all the information that we have available is that Rokov was within limits. Some plants tripped because of Rokov, but just during the last time of the event. Voltages. We're talking even 3 minutes before. The red line is the Spanish limit. The dotted line is the Portugal limit, but the ones that go over the top of this one are in Spain. So in the minutes before the blackout, voltage was a little bit high for 400 kV, but was within the statutory limits. Here you see again the voltage going up and the power exchange with the rest of France and Portugal, in our case, going down. And you see, initially voltage goes flat in 410 and it goes up to 425, by 1233. And remember that the limit is 430, that the limit we have is 435 as you have here. So this is still within the limit. But this is the voltage heat map. You see again how voltage increased in just 1 second. Finally, before the voltage went above the 435 kV, there were some disconnections at this point, and then a lot of generation was lost. There was no capability to control the voltage at that time, and then there was this massive overvoltage and disconnection of the whole system. Again, this bit here, we are talking about 5 seconds. The events have been captured with, this is open source frequency measurements. So you see that the first event was clearly captured, and the following events that we were mentioned were also captured. So we did some small check if the Rokov was enough to cause the tripping, and as I said before, even though some generators tripped on Rokov was not the main cause. I must say that some colleagues that have PV plants, they have a PV plant setting of 0.3 hertz per second for the Rokov, and they tripped on Rokov. And the point is that those PV plants were commissioned long time ago, and they were okay and they were certified at the time. But since then, the regulations have changed, and the protections were set at the Rokov level, correct legally, but too low in that case. And again, this is what the green line would be the frequency in Europe. The blue line is the frequency in Portugal and Spain, and the red line is the voltage level. You see also here some places where clearly the load shedding is trying to keep the frequency, but the amount of load shedding was too much just to be able to survive. And then service restoration. In our place, it took about 6 hours to get the electricity back. Basically, was the time that took for the CCGTs that are nearby to heat up and to get the auxiliaries and to get them online. The whole restoration was about 8 hours. To be honest, I was surprised. I went to buy food for 3 days. Honest, at this point, I didn't think it was going to take only 18 hours for such a big thing. And I think it was a really good job done by the Spanish TSO with the help of the French and Moroccan TSOs. But again, remember that at this time we had, for example, as in the UK, the people in the high-speed trains were stuck in the middle of nowhere in Spain for about 4, 5 to 6 hours, a scorching heat, no food, very little water. So the situation here of these 6 hours on people in transportation is very important just to consider the multimodality of this kind of events as our colleague previously presented. I had some highlights of see how afterwards the Spanish TSO was reacting. I'm not going to go into too much detail, but this is the structure of generation just before the blackout. This is the next couple of days after the blackout. I took these days because the consumption is more or less the same. You see that PV and wind more or less are the same amount. Nuclear power was stripped and it took about 1.5 days, 2 days to go back online. And even here, here it was just a little bit and the power was ramped up. But the main difference is CCGT. You see, CCGT, the production is treble, just to keep more an enhanced safety margin regarding both frequency and voltage control. And exchanges with Portugal went from almost 3 gigawatts to 0. So the Portuguese colleagues didn't trust Spanish colleagues. And that's something that can be seen, but inertia was more or less the same in all cases. So it is clear that wasn't in this case an inertia problem. If you see our colleagues from Portugal, this is the difference in price. If we have the system fully connected, the price in Spain and Portugal should be the same. If we don't have exchanges, prices will be different. So blackout was here. So here there was very little trust or at least the Portugal system operator was playing safe, and little by little we have some trust that has been regained. I have included here, probably will share the presentation with you, and I have included here the initial reports. There's a report from the Spanish government, the Spanish TSO, NSOE, and the Spanish Association of Electricity Generating Companies. More or less, they agree on the sequence of events that I told you. I'm not sure they agree on what is the cause, the main cause. So something that has been said by the Spanish TSO is that some generators didn't comply with the requirements for voltage control. In fact, instead of absorbing reactive power, we're injecting. Some PV plants have been singled out as probably cause of the oscillations, the initial oscillations. The owner is not happy and is contesting that pointing out. And the generating associating are pointing out that at the TSO as responsible for voltage control. Damages are about anything between 2 to 2.5 billion euros. So that's something to do with the way of the report. But it's nice that you have them, so you can have a look at that. Regretfully, the first two and the last one, they are in Spanish. You can use automatic translation, but take care because of some of the new technical nuisances are lost in automatic translation. What is the role of renewable energy? I mean, I'm interested of trying to decarbonize the system. As it was said before, I think the new generation of power system engineers will be the ones that will see the European system, if not fully decarbonized, very, very close to fully decarbonized. So those are challenges that are going to be there for the next few years. So I still think that renewable energy should contribute to voltage control at Black-out. What's the reason? If we want, even right now in Spain and Portugal, we had 70% renewable. And we had this issue. The Spanish grid code does not include renewable, I mean, not renewable because hydro is included, but did not include non-synchronous generator within voltage control as a voltage control service provider. And they didn't consider that also for the service restoration. We had some 10 gigawatts plus something, some 15 gigawatts from the top of my mind of PV and wind that could have been started almost immediately. Obviously, they are following, they are not prepared to contribute to restoration. But even shortening 2 hours, the overall restoration time would have been really, really important. So some of the work we do in some projects is to check what is the possibility of renewable energy contribution to voltage control and Black-out. I'm not going to go into details, so we have done very thorough technical viability studies. I'm very happy that in the UK, mainly we have colleagues that are pioneers in using particularly wind to the renewable systems to the Black-out or to the system restoration for the complete electric system. Yeah, we have some examples that I'm going to go quickly through due to lack of time. So that would be one of the process of system restoration. Again, system restoration from renewables can be usually either sequential, as is has done traditionally, which has some issues, especially energizing transformers, can be done as a soft start, which can take advantage of the power electronic systems and get a much faster and a nicer energization of the skeleton or the black bone. What are the key takings? And I will try to end up shortly. These are some questions that people have made me, and probably have some others. So, was lack of inertia the root cause? I don't think so. It was 30% synchronous generation. Definitely, it was not an inertia. It was faster than that. Is grid forming a solution? When you would see LinkedIn, for example, a lot of people were saying, well, it's low inertia. A lot of people were saying it's because we don't have grid forming. So everyone was trying to put forward what they're working on. So is grid forming a solution? Very likely, but not the only one. The voltage dynamics that you have seen were fast, but we're talking in the range of seconds, not in the range of milliseconds or 1 millisecond. So those could be within the capability of most modern. I don't like to call them grid following converters. I call them more grid supporting, because they don't. It's not only grid following; they do something more. It is important not to forget about the contribution of renewable energy to the overall reactive power and to the control. And also in the blackout in the UK in 2019, September 2019, August, September, one of the issues was some voltage stability issues in Hornsea. So that's something that is going to play a key role in the systems. We have been talking a lot of inertia. Please don't forget voltage. There's a very small experience of grid forming controllers, and those grid forming controllers should be robust and not introduce additional issues. That's important. Also, in Spain and in many other places, we have power solicitation in the grid, but it's not being used in the field. So that was the case in Spain. If renewable energy would have been contributed to power oscillation damping, probably the initial sequence of events could have been avoided. The other issue, how much renewable we can put. I know we were at that time PV plus wind, they were 60%. So the blackout was because of renewables, of course. Play a role, of course they play a role. Anything that was connected at that time played a role, and we need to know in detail what happened with them. Okay, not only the large amount of renewables, but also CCGT, nuclear, etc. Were the protection settings okay? What happened with embedded generation? Remember, we had 8 gigawatts embedded generation that can be switched off very quickly. The same thing that happened in the UK in 2019. It's very little visibility and very little controllability on that amount of a small generation of embedded generation. Should we extend, that was another thing that was said a lot in Spain, should we extend the life of the nuclear power plants to avoid blackouts? Those are two things that are completely independent. One thing is extending the life of the nuclear power plant, and another thing is avoiding blackouts, because those are issues that some people related, but they are completely unrelated. Do we need advanced EMT models? For this case, you see that the dynamics were within the RMS capability. But what was important is that the TSOs stated that some generators didn't behave as they expected. So then this is particularly important. Models should reflect the actual behavior. That's very, very important, because otherwise the decisions, the decisions taken on models that do not reflect the actual behavior can be problematic. What's the safe percentage of PM wind generation? That needs to be studied specifically, but in Spain and Portugal, today they are operating 70% PV plus wind. That this is the same almost every day. So in a system that is almost isolated, 70% would be reasonably safe. Pushing that higher, which would be required if we want to get the decarbonization targets, it gets technically more challenging. What is the way forward? I'm looking forward to the final NSOE report. What is going to be the role of protection settings, operation outside the code limits of some elements, the role of the different switching that happened before the blackout, and even the role of the change of the generator program. Remember, the blackout was at 1233, generator program changed at 1230. Again, there's an urgent modification of the Spanish grid code regarding voltage control. This has gone through the Spanish regulator. It was stopped for about 5 years. It has been going very quickly. Regretfully, 2 days ago, the parliament blocked it. And we'll see what happened. I think probably will go against the parliament. It's very important to use the full capability of converter-based generation, transmission, and storage. Those are very fast events. We have the resources to do that. Has to be done in a competitive way, and has to be done in a robust way. But that's something that is going to be the big way forward, definitely. And something that this is very particular to me. I was surprised that we had no communication for 6-7 hours. When I say no communication, it's zero communication. No telephone, because telephone go on fibers went down, no mobile, etc. So yeah, so we need to increase the backup requirements for telecommunication equipment. That's something going to be very important. Again, how can we? What is the way to increase renewable energy penetration? I said it before. PV, wind, and storage could be considered not as a disturbance, but as a key player to provide voltage stability and frequency stability. Grid forming probably is a way forward. It's not the only way forward. And please use PV, wind, and storage during system restoration. And I have a couple of slides only. Where are we heading to? The situation is going to be even more critical Right now we have 33 gigawatts of wind. We're targeting 50. We have 30 gigawatts of PV. We're going to go up to 135, of which 35 gigawatts will be embedded. Storage, the same. We have 33 gigawatts of storage. We want to go to 12 gigawatts, of which 11 gigawatts will be embedded. So the problem is not going to go to a simple solution. It's going to get more complicated. And this is the same. This is Spain. But if we talk UK, we talk Belgium, we talk Germany, it's the same problem. You see the same numbers going in all the countries. So the main key point will be that use of renewable generation with storage and increased control capability can help decreasing electricity prices, because they can provide these stability system services at a reduced price. And also that should be used during restoration, because you can shorten the restoration time, and that can have very strong impact on social impact on the people who are suffering at taking trains, but also hospitals, etc. Thanks a lot for the for listening to the presentation. And I have here, remember to have. Yes, people started to buy torches and candles. Battery radio was the only way to work. And you need something to cook food, and you need to cash and a good book. Thanks a lot.
Thank you, Professor. Thank you for the expose on the events that happened in Spain. It was really interesting. And right now the mics are opened. From the previous sessions, we had an issue opening the mics, but now we have some questions. Maybe we quickly take them. One of the questions, it's in no particular order, right? One of the questions is about your presentation. It's asking if it's great to see this excellent analysis of the blackout. Is it published? Of course, it's not.
Yes, I mean, we have comments with some colleagues, and we have some more information. We have information that has been passed by generating companies on a sort of confidential basis. But largely, what I have shown is publicly available information. If you want, I can send you the links, and I can send you because in a presentation it's difficult to go through all the small details.
Yes.
The Spanish TSO, sorry, those are the links. These links are active. So if I share the presentation with you, you should be able. The government report is nice because it includes all the part about cybersecurity as well. Because that was when there was the blackout, I went to the street, and one neighbor told me, "Oh, this has been the Russians." So cybersecurity was a concern, was a real concern from the beginning. Okay, and not only in the TSO, it was very clear that the TSO was not attacked, but since the electric system is so high, there was a thorough cybersecurity report, and that's included here, which could be quite nice. The TSO is also quite thorough on the sequence of events and the situations of the different generators, etc. NSOE is nice. I like the NSOE one because it's I'm not going to say less biased, but obviously the Spanish TSO and the generating companies are obviously proving their points, which technically they might be right, but obviously their point of view is different. So I also include that because it's good to have all the information. As I said, regretfully, these two are in Spanish. These three are in Spanish. If you need any kind of help finding out something, I can give you some help. You can go a long way with automatic translation, but some of the technical terms in the power system are translated wrong. Okay, so be careful about that.
Okay, thank you very much. Yuthan, we have a question for you. It says, what do you feel about the timeline for the delivery of a resilient power system in the UK, given the widespread age of the assets we have in the transmission and generation network?
I think that's a brilliant question, and I don't think I'll have a definitive answer here. But certainly what I can point out is this is now definitely at the top of the regulators' agenda, at the government's agenda. They need to try to develop reasonable frameworks that would allow, and standards to allow the operators and owners to actively participating in resilience investment. I think one thing was, for example, last year, Ofgem, the UK's utility regulator, has carried out a consultation with all the system operators, trying to understand how they to elicit a response and feedback on the ideas how they should be embedding resilience in their investment planning or business planning for each of the price control periods. So I think a lot is happening, and a lot should and must happen in the near future in order to really get us prepared. I think I remember one of the feedbacks in a stakeholder workshop I was in is around, we not only require investment to maintain the counter resilience, and we also, because of the changing climate and the more severe and potentially more frequent physical climate risks, we really need to also invest to enhance the resilience of the power infrastructure.
Great. Another question, we quickly take this one, is also for you, Yutan. It says, how do you feel we can improve communications when the public switching telephone networks are being turned off and other communication depends on power?
Again, I think this is a very good question, and I also welcome a professor's response here. I guess I'll respond to the question with another question is, when we talk about blackout type of event, one thing is when you want to mobilize your repair team to attend site to carry out the repairs, but then en route you find out the traffic system has broke down because no traffic lights
Tentei essa, não
working.
foi. Tentei o e-mail, não foi. Não sei também, não. Ele dá, não aceita, né?
Yeah.
Go ahead.
Yes, as I was saying, so there's a whole interconnected dependency system. So there could be the situation you would be stuck on the road because of this no traffic control, not just the communications. Then I think a lot of them need to be thought through, and goes back to what I put in the presentation, preparedness. You really need to thought through what scenarios you are preparing for and how you respond to different types of events.
I totally agree with Etienne. Imagine because when you see it and when you live it, it's a slightly different. These mobile phones are not working. You cannot communicate with the police.
Yes.
Police are everywhere. I don't think they mobilized the army, but police were everywhere and firefighters everywhere, just controlling the traffic in a big city. Because remember that Metro Underground is down as well. Okay, so in the old time, if you have a copper pair, communication between the electricity system, that was okay. Backups were okay. As I said, luckily the backup system, the backup generators for the airports were fine. But that amount of dependency on the electric network is something that should be stressed and is not stressed enough. And the multiple approach to the system is very important. And regarding communications, I'm really upset because there was an old lady who wanted. Imagine you have an old lady that gets in a kind of gets nervous and you want to call the hospital. You won't be able to call the hospital. And this is usually because we have been moving from copper pairs that had a battery backup in the central to fiber, and not even the landlines were operational. So that's something that usually doesn't happen once every 40 years. But when it happens, it's quite serious.
Okay. So thank you very much to our speakers and also to everyone who find time to join this webinar. It was really insightful, and I guess we all learned a lot. I did myself, and I want to say thank you to the organizers from the UK side and the Belgian side. And hopefully we have more of these collaborations to talk about more interesting topics relating to our power system, and then the decarbonization and all of those things, right? So that at least before I retire, it will be much more closer to achieving that goal. So thank you very much, Yutan. Thank you very much, Professor Ramon. It was nice having you guys on the webinar, and I wish you a very good summer.
Thanks all. Bye.
Thank you very much. Thank you. Thank you. Cheers.
Yeah, bye, guys. Yeah.